Let's solve example 4. Here we have another arc length problem where we have different parametric equations, and we're going to use the arc length formula for parametric equations to find the length of the arc of this curve from t equals 0 to t equals 2. So first we'll copy down the equations. The x function here is e to the t minus t. The y function is 4e to the t over 2. And the parameter t ranges from 0 to 2. Now the arc length integral is the integral from t equals alpha to beta of the square root of the x derivative squared plus the y derivative squared, integrating with respect to t. So we have 0 and 2 for the limits of integration, and then we take the square root and we want to square the x derivative. So the x derivative, take the derivative of e to the t, that's still e to the t. The derivative of negative t is just minus 1. We're squaring this, and then we add the derivative of the y function squared. So to do the derivative of this, we have really a chain rule here. The derivative of e to the power is e to the power times the derivative of the power, which will be times 1/2. So first I'm just going to write off to the side here, y prime equals 4 e to the t over 2 times the derivative of t over 2, which is 1/2. So we have 4 over 2 is 2. So 2 e to the t over 2, and that is also squared, integrating with respect to t. This integral describes the arc length of these parametrically defined curves from t equals 0 to t equals 2. Let's work at solving this integral by hand. First thing we want to do is expand inside the square roots, and we want to pay close attention to how this first expression expands because we're going to use a similar concept actually to sort of work backwards. So we're integrating from 0 to 2. And to expand this out, we FOIL. So if you need to take a couple minutes to write down the extra steps, you can do that. But you will get e to the t times e to the t. So e to the t squared, that can be written as e to the 2t, minus 2 times e to the t. Then negative 1 times negative 1 is plus 1. And now we're squaring 2 times e to the t over 2 squared. So 2 squared will become 4. And when we square e to the t over 2, rules of exponents say that we multiply the exponents together. So we have t over 2 times 2. So we're going to get plus 4, that's 2 squared, e to the t. T over 2 times 2 is just t. And we're integrating again with respect to t. So we have the integral from 0 to 2, and we want to simplify inside this square root. Well, we have a minus 2e to the t plus 4e to the t. That simplifies. And I'm going to write that like this. We have e to the 2t plus 2e to the t plus 1 dt. What do we do with this expression? This looks a little bit difficult. Something we want to avoid is just, we can't split it up as the individual square roots of these things. That won't work. So how do we handle this? Well, take a look at this expression from the previous step. Where did this come from? This came from squaring e to the t minus 1. And look at the similarity for this expression. The only difference is that instead of having a minus, we have a plus. Can you see a way to factor this expression here? Think of expanding this expression to get this, and then think of going backwards, factoring. What would we get? Well, we would get e to the t instead of minus 1, we would get e to the t plus 1. So the next step we can write is the integral from 0 to 2, square root of e to the t plus 1 quantity squared. And you can verify if you'd like. If you expand out this e to the t plus 1 squared, FOIL that out, and you'll get this expression here. Now we have the square root of a square. That's very nice. Those cancel, so we have the integral from 0 to 2 of just e to the t plus 1. Look how nicely this simplified. We had really a very unpleasant looking integral to begin with, and after a bit of algebraic simplification, it's quite nice. So the antiderivative of e to the t is e to the t, plus the antiderivative of 1, that's t. We're integrating from 0 to 2, so this is e squared plus 2 minus e to the 0 minus, plus 0. E to the 0 is 1, so we have minus 1 here, and our final answer for the arc length is e squared plus 1. That is the length of the arc of this curve from t equals 0 to t equals 2. Let's look at example 5. This is a bit more conceptual here. We have an integral, which we are told gives the length of some parametric curve as t ranges over an interval. And we want to reverse engineer this. We want to figure out what were the functions that gave us this arc length integral. So we want to figure out the interval for t and parametric equations that would yield this. Now, in general, there's actually multiple possible answers that would work here. So there's not really one single best answer. There's multiple ways that we could express this. And to start, let's write down the formula for arc length in terms of parametric functions. So we have the integral from alpha to beta of the square root, and then the x function derivative squared plus the derivative of the y function squared, integrating with respect to t. So I'm going to view this as the x derivative squared, and I will view this as the y derivative squared. And I think the easiest part here is the interval for t. That's just from 1 to 2. So we can say that the interval right away, t goes from 1 to 2. That gets us the limits of integration. That's the interval for t. Now, how about the rest of this? What is the x function? What is the y function? Well, I'm going to call this first term here the derivative of the x function squared. So I have x prime of t squared equals cosine squared of t. And this tells me that x prime of t could just be cosine. Now, if x prime is cosine, then what is x? Well, to find x, I would actually take the antiderivative of cosine. Because I have the derivative of x, if I want x, I take the antiderivative of x prime. The antiderivative of cosine is sine of t. So the x function that would work here would be x equals sine of t. How about the y function? We'll do something very similar. We'll take this 9 over t squared, and we'll think of that as the y function derivative squared. So y prime of t, quantity squared, we could write as 9 over t squared. If we take square roots here, then y prime of t equals 3 over t. That's the derivative of the y function. So what is the y function itself? Well, the y function itself would be the integral of this. What is the integral of 3 over t? It's 3 natural log of t absolute value. Now, we could add in constants here. We could add sine of t plus a constant. We could add 3 natural log of t plus a constant. That would not be wrong. But we were just told to find any parametric equations. We didn't have to find any specific ones or find them in general. But if we use these parametric equations, along with the interval from 1 to 2, and set up the arc length formula for parametric equations, then we will get exactly this arc length formula, which is what we wanted. Again, there are actually infinitely many valid answers here, but this is one solution, probably the most natural way to solve this problem. So last of all, let's take a look at example 6. Here we will find a surface area using parametric curves. So here's our two parametric equations. We've got the interval for t, and we want to find surface area. So we have the x function t cubed, the y function t squared, our interval for t from 0 to 1. And let's write the surface area formula for parametric curves. We have the integral from alpha to beta of 2 pi times the y function. Here's our y function, times dl, which is the x function derivative squared, plus the y function derivative squared, integrating with respect to t. So we have the integral from alpha to beta, that's from 0 to 1, 2 pi times the y function, t squared. So we just replace the y of t with t squared. And now we need the derivative of the x function, the derivative of the y function. We'll put those in the square root and square them. So we have 3t squared plus 2t squared integrating with respect to t. So this equals the integral from 0 to 1, 2 pi t squared. And let's expand things here in the square root. We're squaring 3t squared. So 3 squared is 9, and t squared squared is t to the 4th. So we have 9t to the 4th plus squaring 2, we get 4t squared. So plus 4t squared dt. Now notice that we can factor out a t squared from both of these terms. So we can write this as the square root of t squared times 9t squared plus 4. If we distribute the t squared, then we'll get exactly what we had in the line above. We're taking the square root of a product. So we can write this as the square root of t squared times the square root of 9t squared plus 4. We can split up a square root in a product like this. So we have the integral from 0 to 1 of 2 pi t times the square root of t squared times the square root of 9t squared plus 4. The square root of t squared is just t. Oops, I forgot a t squared here. So we have t squared times t, that's t cubed. So t cubed times the square root 9t squared plus 4 dt. This is rather unpleasant. This doesn't look particularly nice, and it might be difficult to see what integration technique to use here. We'll go ahead and try u substitution. We'll choose u to be the inner function, and this is going to require back substitution, but eventually we'll be able to get to the answer. So we're going to do u substitution using u equals 9t squared plus 4. So the derivative of u with respect to t is 18t, and this tells us that dt is du divided by 18t. We have a definite integral, so we must transform the limits of integration. So we say if t equals 0, u is 9 times 0 squared plus 4, that's just 0 plus 4. So the corresponding value for u is 4. And then if t equals 1, u is 9 times 1 squared plus 4, that's 13. So the transformed integral is now from 4 to 13, 2 pi t cubed times the square root of u, and dt is du divided by 18t. We can cancel out one factor of t here to have t squared, and then we're kind of stuck. We have the integral from 4 to 13, 2 pi t squared square root of u du. What's the issue here? Well, we have two different variables. The t didn't go away. So sometimes this would tell us that we did the wrong substitution or we did the wrong technique, but in this case, we can actually salvage the problem. Notice that u has a t squared in it. We're going to take this expression for u and solve for t squared. So we're going to solve u equals 9t squared plus 4 for t squared. We'll take that expression for t squared, it'll be in terms of u, and we'll put it into the integral. So u minus 4 equals 9t squared. So t squared equals u minus 4 divided by 9. We'll replace the t squared here with u minus 4 divided by 9. Oh, and I'm forgetting, there's a multiple of 18 that I still have in the denominator, so this should still be over 18. This is honestly a complicated integral. This is about as difficult of a substitution integral as we've ever seen. It's quite involved, but hang in there, we've almost got the final answer. We have the integral from 4 to 13, 2 pi over 18, let's just write that as pi over 9. And then t squared is u minus 4 divided by 9, that's the expression for t squared, times the square root of u du. Now there's a bunch of constants here that I want to take out front. There's the pi over 9, there's this 9 here. I'm going to take all that out front as pi over 81. So there's a pi over 81, that's just a constant I can take out front. Again, that's all this expression here. And so I'm left with, inside the integral, u minus 4 times the square root of u du. It's getting simpler. This is great. Let's keep going. Pi over 81 will distribute the square root of u. So we have u times the square root of u. That's u to the 3/2, and then 4 times the square root of u. So we can write this as u to the 3/2 minus 4 times u to the 1/2 du. We still haven't integrated, but now we have powers of u. Now we can integrate. So we keep the pi over 81 out front, and the integral of u to the 3/2 is u to the 5/2 times 2 over 5, or divided by 5/2, minus 4 times the antiderivative of u to the 1/2, that's u to the 3/2 times 2/3, So we have this. And we're integrating from 4 to 13. So we're going to plug in the 13, then plug in the 4, take the difference. Here's the grand final answer. Pi over 81 times 2, first we plug in 13, 13 to the 5 halves, divided by 5, minus 4 times 2 is 8, 13 to the 3 halves, divided by 3, minus, in parentheses, now we plug in 4. 2 times 4 to the 5 halves, divided by 5, minus 8 times 4 to the 3 halves, divided by 3. Here is the surface area for that rotated shape, and this is approximately equal to 4.94 if we plug it in a calculator. So there we have it. Now, I don't know about you, but I feel exhausted after working through this entire integral. A lot of times in these sections, the main point is to get to the integral expression, and we won't actually worry about solving the integral. So the main point here is really to understand how to use the formula to get to this step here, but it was good practice to work through this very complicated substitution problem, and we got the correct answer in the end.